This is your invitation to leap ahead in your engineering career. The inaugural Product Development Expo, PDX, happening in Phoenix, Arizona on Tuesday, May 14th, 2024, brings you face-to-face with the engineering elite. These aren't just any speakers, they're the industry's highest performing product development engineers, ready to share the methods and strategies that have defined their success. Imagine learning design for manufacturability from those who've redefined it, diving deep into tolerance analysis with pioneers, exploring novel engineering applications for Excel, and unlocking unique 3D printing strategies all in one place. These high-caliber engineers will open their playbooks, offering practical, hands-on lessons forged over decades in the trenches of innovation. Don't miss out on this unparalleled opportunity to absorb the wisdom of those who've led the charge in engineering breakthroughs. PDX is your chance to not just meet but learn directly from these legends of engineering. Mark the date, May 14th, 2024, in Phoenix. Elevate your skills, ignite your creativity, and join a community of growth-minded engineering professionals at PDX. Learn more at teampipeline.us/PDX. Hello and welcome to another exciting episode of the Being an Engineer podcast. Today we are thrilled to welcome Krishna Raichur, a principal engineer at SimuTech Group and an Ansys certified elite channel partner. With a robust career spanning over 3 decades, Krishna has made significant contributions to the field of engineering simulation, technical support, and techno-marketing. His expertise in Ansys products and his passion for educating others make him a distinguished figure in the engineering community. As we delve into Krishna's journey, we'll explore his insights into simulation technologies, the evolution of engineering tools, and the impact of digital twins and AI/ML algorithms on the industry. Krishna, thank you so much for being with us today.
Thank you for having me, Aaron.
What made you decide to become an engineer?
Good question. Well, growing up in India in the 70s, of course, I'm dating myself right here. Back then, we were kind of groomed to become either a doctor or an engineer, or you were considered a bum, kind of, Of course, that's kind of tongue in cheek there, but
Sure.
you know what I mean. It was really doctor or engineer were the main things. And I was always kind of fiddling around with things. We used to have what is known as what we used to call a mechano set. Think of it like a Lego set, but it's more links and bolts and nuts, and you could put them all together to make a car or a plane or and things like that. And me and my cousins, we would play with the mechano set all the time. We're also interested in dismantling and then assembling things. I had a bicycle, and for no reason at all, I would just dismantle the whole thing and start reassembling it just for the heck of it. So I guess I was kind of an engineer to begin with in that way, and eventually said mechanical engineering is the way to go.
Yeah, it sounds like you were destined to become an engineer. There was no way around it.
Right.
It's interesting hearing about in India where you were groomed. I know it was kind of tongue in cheek, but either to become a doctor or an engineer. I feel like here in the US, it's often a doctor or a lawyer. An engineer isn't discussed quite as much. Why do you think that was? I mean, maybe a little bit of speculation on your part.
Yeah, it's going to be speculation, but really, back of course, things have changed now big time in India. I think doctor engineer may actually be looked down upon almost. I don't know for sure because I haven't been in that society for a while now. But, back then, really, law was, considered not very glamorous, shall we say.
Hmm.
and whereas, doctor, there's always glamour as a doctor. I don't know if glamour is the right word, or prestige maybe the right word.
Sure. Yeah.
And engineers, same thing, they were looked up to, engineers and so on. And so that's how it was. I don't know why that was the case. Surely in this country, lawyers and doctors make a lot of money compared to engineers, but I think back then in India, doctors and engineers were really the ones making the money.
Very interesting. Ah, okay. Well, great. Thank you for sharing that. So you are an expert when it comes to simulation and simulation related technologies. Can you share a little bit about how that came to be? What was it that influenced you to move your career in that direction?
It's interesting when I was not really exposed to finite elements until I came to the US to do my master's degree in mechanical engineering. I went to Villanova University, and in the very first semester, there was a finite element course. And funny story there. Here I am, brand new to the country, still trying to understand accents, the American accent and everything. And the professor was a great guy, a great professor for finite elements. He had this southern drawl, and for the life of me, I could not understand a word he was saying, except when he wrote on the blackboard. I could not really follow this guy. He had the southern drawl, and I was almost sure I would flunk out of this class. I was really scared. But to my surprise, I did very well in that class, at the end of the semester. And then this uh, professor, he actually introduced us to Ansys at that time. And of course, this is way back in the mid 80s, and Ansys was still at a very young age, if you will, all command based and things like that. He introduced us to Ansys, and I kind of picked up on it, and I got good enough with all the commands that he asked me to teach newer students. Hey, why don't you get them up to speed with Ansys, kind of thing. And In my final semester, I decided to do what is called an independent study, which is a little bit less of a commitment than a thesis, right? A full-fledged thesis. Decided to do an independent study with this professor. He had a particular problem that he was looking to solve. He said, well, if you're up to it, let's go. And so that's when I started using more of Ansys. And interestingly, around that time, of course, I'm looking for jobs, and there was an announcement, or in the bulletin board, I saw that there was a technical support position open at Swanson Analysis Systems. That's what Ansys was called before it was called Ansys Incorporated. Now, back then it was called Swanson Analysis Systems, and I saw this ad, and I applied for it, and thankfully I got a job, and the rest, as they say, is history. So
Wonderful, wonderful. Well, what an exciting moment that must have been as a young engineer. So you've kind of seen a lot in your career when it comes to simulation and how engineers work with and implement simulation
yes.
in their jobs. What are some of the challenges that you've seen engineering teams facing when trying to implement these simulation technologies into workflows that maybe previously, were more like hand calculation or maybe just
Right.
engineers' gut instinct?
Correct. Actually, the biggest challenge, I think, is resistance to change. Kind of we've always done it this way type of thinking, right? Um, and there was a time when the challenge was to make customers aware. I'm talking, 90s and maybe even the early 2000s. Um, the challenge was to make customers aware of the benefits of simulation. Okay. I want to say maybe 80s and 90s. They were so used to physical testing and, like you said, hand calculations and so on, and they thought they couldn't trust results from a computer simulation. Of course, we've come a long way from then. Now, most customers understand the importance and benefits of simulation. Now the challenge is to make them uh, have simulation be more of an integral part of their design process rather than an afterthought type thing, and also moving simulation from the component level to the system level. This component may behave very well or show itself to behave very well on my, in isolation, but when it's part of a system with other devices, you know, working hand in hand with this component, how is it going to behave? So moving up to the system level is now more of the challenge, and Ansys has really products that can help with that, and we are trying to help our customers do that. So really, the way to overcome, really, I think it boils down to education, showing case studies, teach customers to do their own case study. And a lot of times it's not just the technical part. We also need to educate the finance team and show them the ROI, if you will, of incorporating these technologies.
Yeah. So speaking of case studies, can you think of a project where the application of Ansys tools directly contributed to, a breakthrough or some significant improvement in the design or performance of a product?
Oh yeah, there are many stories along those lines, but one that comes to mind is one of my colleagues. I was talking to him recently. He worked on a CFD simulation of an artificial heart. And this is like a total artificial heart, not just one portion of the heart or like just the left ventricle or just one valve or something. This is the entire or total artificial heart, they call it. It works without any valves, and it stays suspended with forces from magnetic forces and hydrodynamic forces balancing each other out. And basically, like our real heart, it has a left impeller and a right impeller in place of the left ventricle and the right ventricle. Now, when they tested this initial device in animals, they found blood clots on the right impeller after about a month. And there were no clots on the left impeller. So that's where CFD simulations came in, and my colleague and his team got together. They figured out that the lower shear stress levels on the right impeller walls corresponded to blood clot locations. So meaning if the blood is just sitting there not moving much, it tended to form clots, and they found these more and more on the right impeller, none on the left impeller. So apparently there's a sweet spot for these shear stress levels. If it's too low, you will get blood clots. If it's too high, will destroy the red blood cells and platelets. So it has to be somewhere in between. So to get that sweet spot, they used, CFD simulations, computational fluid dynamics simulations, to try different configurations of the, positioning of the impeller blades, the angle of those blades, and so on, and came up with an improved design. And now they have conducted some preliminary testing of this new pump design. The good news is that new pump has a more efficient right impeller design. It can operate at lower rotational speeds, meaning it will reduce the likelihood of damage to the blood, red blood cells, and so on. They have not yet conducted enough animal experiments to determine the impact on the blood clots and so on, but it does look promising. So I thought that is something fantastic, with the heart disease and all this and artificial hearts. It's something great.
That is phenomenal. What a great case study.
Yeah.
I guess I didn't realize the level of, I don't know what the right word to use is, not quite fidelity, but that you could simulate tissue that accurately to the point where the software can determine or at least make indications of whether blood clots are going to form or not. That is fascinating.
Yes, that's quite a challenge, actually, getting the right material properties for the tissue and so on. Thankfully, in this particular case, this was a man-made artificial heart with a motor and all the stuff. So they didn't have to worry so much about tissue, but still you're right.
Right.
Once it's
Good point.
incorporated in the human body or in the animal body, you have to model the surrounding tissue as well.
Yeah. Okay. Let's use that and back up just a little bit. Can you explain, not getting super technical here, but in as basic terms as possible, what is simulation? For those who just have not been exposed to it at all, you use the term CFD, computational fluid dynamics, there's FEA. What are these things? What does simulation mean and how does it work?
Well, to put it in very basic terms, I think of simulation as virtual testing. So, let's say you have a design that you come up with. The traditional way would be to make prototypes of this design, take it into the lab, and subject it to whatever loadings you expect it to see in the real world, and then seeing if it's going to withstand those loads. And that has always been there, and it's still going to be there. What simulation does is take that testing part onto the computer. So what we do is we create a mathematical model of that whatever device it is. Maybe it's a hammer, it's a wrench, or it's an artificial heart, whatever it is that you're designing. You would make a mathematical model of it, and you would apply those loads mathematically on the computer. And there is techniques, numerical techniques that will allow the computer to calculate how this device responds to those loads. And then you can look at it on your computer and say, well, in this particular location, looks like this thing is deflecting too much, or the stresses are too high, or the blood is flowing too fast here in this location, or there's not enough blood flow here. Whatever, you can visualize all that on the computer. And since you're on the computer, you're free to make whatever changes you want without having to build new things, go back to the lab, right? So you can try different designs on the computer. Well, let me try repositioning this vein on this impeller this way and see how that affects the blood flow, whatever it is, right? So you can do those things much faster on the computer and try different designs much faster. And then you can come to a final design and you can say, well, this is looking really good. Now let me build a prototype of this one thing, not the 20 other things that I tried. I'll try this one thing and I'll build it and I'll test it. And maybe instead of running 20 tests, you just run one or two tests. That's really what simulation is all about.
And ones and zeros are a whole lot less expensive, generally speaking, than custom stainless steel parts, right?
Absolutely. Absolutely.
Yes. Okay. What are some common misconceptions about simulation that you encounter, and how do you go about addressing those?
The most common misconception is that simulation is for PhDs, and that it's difficult to learn. I need to be a real engineering guru, a PhD to take advantage of it. And maybe back in the day, when simulation or finite element techniques first came about, maybe that was the case, but not anymore. So it's not as difficult to learn because of improvements in technology. The other misconception people typically have is that it takes too long, to not only to learn, but also just to implement simulation and so on. And again, with the advances in computer technology and so on, that's no longer an issue. And today, the most common misconception we run into is, well, I want this simulation to replicate exactly what I'm seeing in the lab, the test results. And, because in the lab, there are so many possibilities, right? There's the environmental conditions and stuff like that. And all those things are very difficult to duplicate in a computer model. So it's trying to get engineers to understand that, hey, you won't be exactly replicating your physical test. If you do want to do it, it'll take quite a bit of a model to do it to um, I guess duplicate the exact conditions that you're testing it in. So why don't you just not worry about the test results so much, but make sure your model is representing your true physical conditions as much as possible. So I don't know if that answers the questions, but those are the typical things we run into.
Okay, great. I don't know how easy it will be to answer this next question, because the answer, I'm sure, is it depends. But what kind of performance, like processing power, does one typically need on the computer, the system they're using for simulation? Can you get by with a nice laptop these days, or do you need to have like a server farm available to you to run all of those calculations?
It's a good question. It really can be anywhere in between, anything from a laptop to a server farm and anything in between. Because a lot of times what happens is you want to start your analysis with simple, small models just to prove out the fact that my model is behaving as it's supposed to. And so for that, you don't need a server farm. A laptop will do with some, you know, not a home laptop, but a little bit more of a power in your laptop in terms of memory and so on. But a laptop should do for a lot of the basic, simple analyses. But today, what's happening, this trend today is to model not just a single component, but an entire assembly, an entire machine, for example, not just one component of a machine. So if you want to do that, now, of course, you need more horsepower to do that. And that's where we get into server farms and so on. And the other thing is it also depends on the type of physics you're solving. If you're solving a computational fluid dynamics problem, like that blood flow we were talking about earlier, you'll probably need more horsepower than if you're modeling, maybe a wrench or a hammer or something like that. That may take lesser computational power. So it depends on the physics that you're solving as well.
Okay, fair enough. Yeah. Well, let me take a short break here and share with the listeners that our company, Pipeline Design and Engineering, we develop new and innovative manufacturing processes for complex products and then implement them into manual fixtures or fully automated machines to dramatically reduce production costs and improve production yields for OEMs. And today we have the privilege of speaking with Krishna Raichur. Krishna, can you explain the concept of digital twins and how they're used in engineering these days?
Yeah, different people have different definitions of a digital twin. Some people say my finite element model is a digital twin, but where the way Ansys defines a digital twin is it's a combination of a physical device or asset with a simulation model. So for example, think of a critical component like an engine or a pump. What we do is we put some sensors on it that can measure information that's happening in real time, like maybe the temperature or humidity or the movement or whatever it is you want to measure, acceleration, whatever it is you want to measure, you put some sensors on it. And then, of course, you build a computer model, a finite element model of that same device on your computer. Right now, what the digital twin concept is, the computer model is getting real-time data from these sensors and, churning out results very, very quickly. These are models that are designed to run in seconds. Okay, we call them reduced order models. And they're designed to run in seconds. They get the information from these sensors, what the current temperature is, what the humidity level is, whatever it is information that your model needs. It gets that, spits out the performance parameters of your device in real time. And then the engineer can decide based on the results, hey, is this overheating? Do I need to maybe stop this pump or this engine, uh, you know, in a short while so I can do some maintenance work on it, rather than waiting for things to fail and then you get into expensive repairs and shutdowns and all the stuff. So it helps with that real time, simulation based on real time data.
Okay. And it also serves as kind of a secondary check, right? I mean, if you have a physical part and you test it, you get some results, and then you test that same digital twin within a simulation environment and you get different results. Now all of a sudden you have a pause, right? A hold on, something's not right here, whether it was a mistake in the test on the physical part, or maybe the boundary conditions in the simulation were set up incorrectly, but it gives you kind of a backup test just to make sure, especially on mission critical parts, that the test data you're seeing is in fact accurate and reliable test data. Is that correct?
That is correct. Absolutely correct. So what they do with these, I mentioned reduced order models that spit out answers in seconds. What they do is they tweak these models to make sure that it is as close to the physical asset as possible.
Nice. Okay. I certainly am no expert when it comes to simulation, but I've dabbled with very, very basic, static simulations. And I know some people who that's what they do for their job is simulation work. And so I've had a few conversations about this. And what I've gleaned is that simulations with, and specifically FEA I'm talking about, I don't know anything really about CFD, but, with when it comes to FEA, simulating metals can be easier and the results can be more straightforward than simulating plastics. Is that generally the case?
Yes and no, if I may say so. And what I mean by that is, from an actual underlying technology standpoint, metal finite element models will be the same as plastic finite element models. The tough part is because there are so many varieties of plastics, right? Getting the material properties of a plastic characterized is a little bit more of a challenge compared to a metal, because metals have been around for a long time and people have, years and years of test data that they can come back to and rely on, saying, well, I'm using stainless steel 300, whatever it is, and I know these are the material properties. With plastics, it can be so varied, and so it's what is the challenge is really the characterizing the material properties of a plastic. If you can characterize the material well, then your finite element model will predict the correct answers.
Okay. How about, can you explain the difference, again, within the context of FEA, between a static simulation and a dynamic simulation?
All right. So a good way to think about it is, think of a diver standing at the end of a diving board, just standing still. Okay. Obviously, the weight of the diver is going to, bend that diving board somewhat, right? And so that to calculate the deflection and the stresses in that diving board with this person standing still at the end of the diving board, that would be a static analysis. Now let's say this diver is jumping before he takes the dive, he or she takes the dive. Let's say this diver is jumping up and down on this diving board. Now you can imagine this diving board kind of vibrating up and down, right? And then the person hits the diving board and then leaps into the water. Well, if you now want to calculate the whether this diving board can withstand that type of a load, this person jumping up and down, a static analysis is not going to be sufficient. You need a dynamic analysis because there is the inertia of this person going up and down, that's going to be taken into account, which a static analysis does not. I guess that's the simplest way I can explain it.
Perfect explanation. Thank you. I had a question in mind and I just lost it. What was it? It'll come back to me. Well, what's one piece of technical advice that you often give that you wish more engineers would implement into their daily work?
Well, most common one that I give and my colleagues give to our customers is to start with simple models and add complexity as you go. I can't tell you how many times we get support calls where the engineer has built this enormous model with, a gazillion elements in it, and then it's not working. And it's with a large model like that, it'll take a long time to complete the solution. And then it may not even complete after running for a long time because of some issue with the way you modeled it. So we always tell people, well, can you make a simpler model just to make sure it's working right? And then slowly add complexity. Like that diving board example, right? Start with a static analysis and then incorporate the dynamic loading of this person jumping up and down. Don't directly go into that dynamic analysis because it'll be hard to, debug your model, if you will.
Got it. Okay, great. How about, no tool is perfect for every single situation. What are some of the limitations on simulation that engineers should be aware of and cautious of?
That's a great question. Really, the limitations would be material characterization, meaning if a basic requirement for your finite element simulation, for example, is, have I characterized the material properly? For example, I have a steel part, a rubber part, and maybe a plastic handle or something on this device that I'm modeling. Well, have I modeled the material properly of this rubber? They're just like plastics. There are many, many different varieties of rubber. Have I characterized the rubber properly? Okay. So really, that would be one of the important things I would recommend people to look at is make sure that you have the right material characterization. And then the other, I don't want to call it limitation, but the other important thing you have to consider is, we apply these loads mathematically on the model. Do these loads, are they representative of the real load that is being applied to this model? And going back to that diving board example of this person jumping up and down, how well can we characterize that up and down jumping on this diving board? If you can characterize that, and you can, of course, characterize it quite well, and as long as you do that well, you can rely on your results. So really, it boils down to, does my model represent, physical reality fully?
Yeah. Okay. You had mentioned before that one of the misconceptions about simulation is that it takes a long time to learn. It's really, really hard, and it's going to take forever to figure out how to use this tool. These days, with the modern tools that we have and the training that's available, how long should an engineer expect to get to like a basic level of competency? Not like a world famous guru or anything, but, good enough that he or she can run some simulations and be confident in the basic results.
So, with a good engineering understanding of engineering fundamentals, I think that is important to understand the engineering fundamentals. What is stress? What is strain? That kind of stuff, basic stuff. As long as you understand the engineering fundamentals, picking up an engineering simulation really these days shouldn't take more than, I want to say, a day or two, really. Um, Getting familiar with the software, what buttons are where, and uh, you know, we have what we call getting started quickly type of courses or quick start courses on our website where literally, in a half a day, they would be running some basic models. So yeah, I would say about a half a day.
Terrific. Okay. You had also mentioned earlier about ROI, right? How is this actually going to save us money? Is there a story that you can share or a case study experience where using simulation really reduced the cost of a development program? And if there isn't a specific story, then maybe you could speak to just generally, like, how should engineers think about the ROI when considering simulation?
Yeah, see, the biggest benefit of simulation is that you can run hundreds of test cases on the computer without ever, building a single part. And so right there, the ROI is huge, right? Instead of building 20 prototypes, each of which may cost, I don't know, hundreds of dollars, okay, you run those 20 prototypes on your computer, which costs, other than the cost for the software itself, you're not spending any money building those parts or those toolings and all that stuff. So right there is a huge, huge saving. So, it's almost a no-brainer to consider simulation as to be an integral part of your design process.
Great. So, regarding the cost of the software itself, not specific to SimuTech as a channel partner or anything, but I imagine the cost to get into simulation is roughly the equivalent no matter where you go to purchase that software. Can you give the listeners a general sense of the costs involved? What's the investment to get involved with simulation?
So at the lower end of simulation, you can get basic simulations done for, I want to say, three-figure investment, right? Like maybe under $10,000. Let's put it that way. Okay, and then as you want to explore higher and higher levels of simulation, like that example I gave you of, the one where, what was that example? I'm just drawing a blank on it. But
the artificial heart.
Yeah, the artificial heart example. Well, now you're looking at higher level of simulation, right? You have fluid flow happening and all the stuff. So that one would take a lot more investment in the software and so on. So it really can vary from three figures to six figures. Okay. So it depends on exactly what you want to do.
Okay. And like most things, of course, you could hire this out, have a group. Maybe you're not using simulation regularly, but you have a project or even just a specific application within a project where you really do need it. You could hire it out, or if you're doing a lot of simulation work, it might make sense to just purchase the software outright and then your team can use it over and over and over. Is there like a break-even point that teams should be aware of when they're thinking about just contracting that work out versus purchasing the software and training their staff internally? How should they think about that?
That's a great question. It really depends on the philosophy of a particular, customer, right? How they think about it. Some customers are in the mindset of, well, if I'm going to do it, I'll do it myself, even if it takes me some time to learn it. And then on the other end of the spectrum, there may be customers who say, well, I don't want to get into, you know, simulation business. We have experts who can do it and give us the answer. So I would rather do that. So, you know, it's both ends of the spectrum really. And it really depends on what your intent is. And like you said, if it's like a one-off, simulation that you need to do to satisfy some government requirement or something like that, maybe it would make more sense to, send it out as a consulting project for a company. But if it's something that you need to do on a regular basis, maybe it's not a one-off thing. Maybe you need to run these tests constantly on every design that you have. Well, in that case, it makes sense to bring the software in-house and have a trained engineer or a trained team of engineers to run the software.
And there are different levels and packages that you can get with simulation. What's the kind of like the ballpark range that companies should expect to invest to get, a license of these, whether it's just FEA or a CFD or different levels? Is it like $5,000 to $20,000, or does it vary, even more than that?
Yeah, so at the lower end, for some basic simulations, you can get away with, $5,000 to $10,000, $15,000 range. And then if you want to get into really, high fidelity simulations, and you want to do what we call multiple physics, you may be interested in not just stresses and deflections. You may also be interested in fluid flow and like that pump we were talking about. You may be interested in fluid flow. You may be interested in the electromagnetic behavior of things. Maybe you're designing a satellite and you want to see how well the satellite behaves, and so on. So depending on the type of physics you're doing, it could be, multiple six figures that you may need to spend. So it's really a huge range.
Just for the software.
Just for the software, yeah.
Interesting. I did not know it could range that greatly. That's really interesting. Okay, great. Well, let's see. I think I have one more question and then we can wrap things up here. What do you see changing in the future of simulation? Obviously, it's come a long, long ways since the command prompt days back in the 80s. Looking out into the next 5-10 years, what do you see as the next evolutions of simulation?
I think where we're heading is really artificial intelligence and so-called machine learning. Okay. Where the idea is to feed the years and years of experience that people have with their models into computers and let the computers kind of come up with answers very, very quickly. Okay, so you have the potential to solve highly complex simulations in a matter of seconds just because of the history that you have, and so on. So with artificial intelligence, machine learning, I would think that's the next frontier. And already, we have made some strides in that direction.
Very cool. That is super exciting. Anything we can do to make that work just a little bit easier, a little bit faster, a little bit more straightforward. Okay. Well, Krishna, what a pleasure it's been to speak with you today and hear all about simulation and the different tools available to engineers in that category. Is there anything else that we haven't talked about that you think would be useful for engineering teams out there to know about simulation?
I think the main thing is don't be intimidated by simulation. Just like today, CAD software, computer-aided design, is considered an integral part of almost any design type work. We should think of simulation as equally, in the same ballpark as computer-aided design, CAD software and so on. Simulations should be in the same category, treated in almost in the same category, because it's so important, I think, to do simulations up front.
Terrific. Okay. Well, Krishna, how can people get in touch with you?
Well, they can get in touch with us, with our company, info@simutechgroup.com would be one way to get in touch with our company. And of course, I am on LinkedIn, Krishna Raichur, look it up. And not very, very active on LinkedIn, but I'll be glad to interact with anybody who would like to on LinkedIn.
Terrific. And we will put the email address of SimuTech as well as the website URL and Krishna, your personal LinkedIn URL in the show notes here. So everyone will have direct access to that. Okay. Well, Krishna, thank you again so much for being with us today on the Being an Engineer podcast.
Thank you for having me.
I'm Aaron Monker, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing turnkey equipment, custom fixtures, and automated machines, and with product design, visit us at teampipeline.us. Thanks for listening.